Good afternoon, dear participant, and welcome back to 10th session on the control theory, control system design. It is my pleasure to welcome you back to our ongoing faculty development program. Today, we are excited to commence the 10th session, focusing on the pivotal topic of control system design. Over the past sessions, we have explored various facets of engineering and technology, delving into the depth of innovation and practical applications. Today's session promises to be equally enriching, offering insight into the principles and practices of control system, a cornerstone of modern engineering. Control system design is integral to ensuring the stability, performance, and efficiency of dynamic process across various industries, from aerospace to automotive and from industrial automation to robotics. Our session today will provide a comprehensive overview of the latest technologies and methodologies, equipping you with the knowledge to implement robust and effective control strategies. We are fortunate to have with us as an esteemed expert in the field. We will guide who will guide us through the intricacies of control system. Their expertise and experience will undoubtedly provide valuable learning opportunities and foster a deeper understanding of this critical area. Today, the resource person will be Pickon Majumdar. He is dedicated and skilled software application engineer with extensive experience in emerging technologies and electrical engineering. With a BTech in electrical engineering from WBUT and an MTech in illumination technologies and design from Jambheswar University, he has worked in various roles, including software application engineering at Elmax system and solutions lightning consultant at Intel Lux Electronic Private Limited. He has contributed significantly to research and development project, and his expertise spans machine learning, deep learning, digital image processing, IoT, and more. He is also pursuing an MBA from Manipal University, Jaipur, showcasing his commitment to continuous learning and professional growth. So I would like to now invite to Pickon Majumdar. Welcome to this session, and over to you, sir.
Thank you, sir. Thank you for introducing me. Sir, my voice is properly audible and my screen is visible?
Yes, sir. Yes, sir.
Okay.
Screen is visible and
Okay.
voice is also very clear. And I also
Okay,
ask to the participant, you can unmute during the session. If you have any kind of query, you are allowed to unmute the mic. Just 1 minute. Yes, during the session, anyone can unmute your mic for any query so that this session can be more interactive. Dear sir, also I request you first to unmute your mic. Your mic is muted.
yes, sir.
Yeah, now it's okay.
Okay. So, thank you, sir. And good afternoon, participants. Myself, Pickon Majumdar, and I am the application engineer in MATLAB. And today, my presentation, my discussion is basically on control system, and sir is already has already divulged that how we can design a control system, what are the key areas of control system, and what are the advanced technology. So where we can incorporate the control techniques, advanced control techniques that we discuss in this session. Okay. So Yes. So in brief, so to basically our focus on MATLAB, because the session is basically the MATLAB based presentations, how we can solve different control techniques using MATLAB platform. So there are different types of apps are there, toolboxes are there, which basically very helpful for system design and simulations. So that thing we will I will discuss one by one. Okay. So initially, I can say that the control system is a very important topic, very important for all the engineers, and basically the significant control for different devices. If you want to control any motor, or if you want to control the temperature, okay, ambient temperature in a indoor room. So there you can use the control system options. Also, the sir has already discussed, already told the stability. So stability is basically the main area where we should apply the control system. If I consider a system, a system should be controlled. A control system basically a device, or you can say that it is a set of devices. Set of devices means what? There must be some hardwares like controller or the sensor, controller and the sensor, and that devices basically manages or directs or regulates the behavior of the other devices or the system. Okay, so this is the control system, and if I am talking about the basic component of the control system, so from this slide, you can say that this is the system, this is the control system, where we can apply the input of the stimulus, and from here we can get the output. So from here we try to apply the desired response, and after that we can eventually find out the actual response. Okay, so our prime objective should be like that way, that the desired output and the actual output will be equal. Okay, so on the basis of that we can design a good control system. Okay, so here uh, the basic feature of the good control system, that it will generate a response quickly, and without oscillations it will reach to its steady state behavior. There should be the good transient response, and of course the steady state error must be low. Steady state error is a low error once it is settled. So if you apply the stimulus to the plant, to the system, so at that point of time there is two types of behavior will generate. One is the transient behavior, another is and after a certain time, I mean the 5 second or 10 second, it will reach to the steady state behavior. So one is the transient response, another is the steady state response. So we should keep in mind that we should design the system in such a way that the actual output and the desired output, the error between the actual output and desired output must be low. Okay, so if there is a low error or low steady state error, then we can consider the system as a good control system. Okay, next thing is that and we it will not oscillate wildly or damage the system. Because if we apply any input, so there must be some oscillation, so we should maintain the stability. Okay, so this type of system, this control system basically comprised of some basic components, though it is not mentioned here. But if I am talking about, suppose I want to control the ambient temperature of a room. Okay, so ambient temperature of a room, or if I am talking about the air conditioner system. Okay, so we are providing the input, Input means we are providing AC voltage or electrical signal to the system, and finally a temperature is generated. Okay, now the temperature is compared with the surrounding. Okay, so if it is at 18 degrees centigrade, if it is below 18 degrees centigrade, the relay will cut for a certain time. Okay, so that kind of system or that kind of technology is incorporated. For this for build that kind of system, some kind of controller is required, some specific controller is required, some sensor is required. So this is basically the basic components of a control system. So if I am talking about sensor, suppose here if I want to compare the output, actual output with the desired output, or actual response to the desired response, there must be some sensor. So sensor is basically the device that actually measure the physical quantity, like you can consider as a temperature, or you can consider as a pressure, or if I am talking about the speed control of a DC motor. Okay, so at that point of time, the position, angular position, so which can be represented by theta. So this is basically the physical quantity which should be converted into the electrical signal. So sensor is the device that actually measures the physical quantity and convert it into the electrical signal. This is the one thing. Another thing is that the controller. So here you can see that this is the design cycle. So you have to determine a physical system and specifications from the requirement. So in this requirement also we can include the controller. So controller is basically the component that processes the signal from the sensor. Okay, so here you can see. So here you can see this is the example of the PID controller. PID stands for proportional, integral, and derivative control. Okay, so I will discuss on it. Okay, so and here you can see that this is a plant or the processor. Okay, so now here the RT stands for the reference input, and YT stands for the output. Okay, control output, you can call it as a control output. Basically not YT, basically generally it is represented by CT. So CT is the control output in time domain, RT is the reference input in time domain, and here you can see that this is the summing amplifier or the error detector. Okay, so here plus, this sign is minus, so generally it will generate the error signal. So error signal in time domain, ET. Now this ET is goes to the controller. So PID stands for the proportional, integral, and derivative controller. Okay, so here you can see that while it to control the output from the plant, or control the generated output from the plant or the processor. Okay, so we have to use the controller before that. Okay, so this is the controller. This is the controller which basically processes the signal from the sensor, and it will generate the output signal to the um, uh, to control the actuator. So if I consider the actuator as motor, okay, so we can control the speed of that motor, okay, by using the PID control techniques. Okay, now what is actuator? If I am talking about the actuator or the final element or the final device, so which we try to control, so these devices basically convert the output signal from the controller, and it will convert into the physical signal. Suppose uh, opening a valve, if I want to open and close a valve, okay, in a control manner. So or if we want to control the speed of the DC motor or adjusting the heater, so at that point of time we should use some sensor as well as the some controller. Okay, so this is the basic idea of the control system. So this is the design cycle. First we determine the physical system and specifications from the requirement. Then we draw the functional block diagram. Basically, whatever be my system. Suppose I am talking about the RLC circuit. So RLC, this registered inductor capacitor, is basically the physical form of a network. Okay. So now if I want to represent in a block diagram based presentation, then we can do that way. Okay. So after that, we can transform the physical system into the schematic. Okay. So in a schematic we can transform it, and after that the signal flow. So you can see that the signal flow is in a particular directions. Okay, not in a haphazard manner. So if I consider this is my reference input, okay, so the flow is like that way. So this is the unidirectional. You can see that unidirectional, and after that it will reach here yt. Okay. So if there is a multiple blocks, if there is a multiple blocks, so here you can consider these are basically the blocks. Okay. So if I considered this is a multiple block for a closed loop system, we can use the block diagram reductions technique. So to reduce the number of blocks, and finally we analyze and test the system under all conditions. Okay. So now from this figure, you can see that this is the dynamic response of a system. So if we apply any type of signal, like step signal, or the ramp signal, or impulse signal. Okay, so at that point of time, it will show two type of response. One is called the transient response, another is called the steady state response. So here you can see that this is the response versus time, response versus time graph. Okay, so as the time is increasing, okay, so increasing, you can see that after a certain time it will reach to the steady state condition. So here you can see that this is my actual output, and this is my desired output. Okay, so this is my input command. So if we subtract it, then you will get the ESS stands for the steady state error. Okay, so now next thing is the two type of diagram is here. One is the two type of control system is there. One is called the open loop control system, another is called the closed loop control system. So what is open loop control system? It is very easy. That here you can see that there is no feedback or no closed path is there. So without feedback or non-feedback control system is basically called as the open loop control system. Okay, so here you can see that if you see here, there is a closed path. Okay, so this is called the feedback path. Okay, but here you can see there is a no feedback path. So without feedback path, this is called the open loop control system. And in this open loop control system, basically the control action is independent of the desired output or the controllable output. So here you can see that this is our output. Okay, or the controllable variable. Okay, so and this control action is basically independent of the desired output. You can apply your input, but here you can get a certain output. Okay, so but in case of open loop control system, here you can see that you can apply the you can use the transducer as well as the controller. So this is called the summing junction. Okay, so main advantage of this open loop control system is that so you can easily design that kind of system. It is very simple in design, and it is economical, or the calibration problem is less. But in case of closed loop control system, here you can see this is my reference input that is represented by RT. Okay, so in previous slide, I think you have observed that this is in my previous slide, it is the RT. Okay, next here of course this is my plant or the process. Okay, and before that you can use the controller. Okay, you can use the controller. So in case of closed loop control system, this type of design is little bit difficult to build. Okay, but due to the presence of feedback control, feedback path, the output is basically accurate. Okay, so in case of closed loop control system, the accurate result or accurate outcome will be there. Okay, and it is of course reliable, and the optimization is possible here. Okay, now just this is a um, representation. This is a representation or the diagram, or you can call it as a control system design for motor speed control. Okay, so if I am talking about the motor speed control, definitely you know that motor is basically the machine which can not device we can call it as a machine, because it is a electromechanical energy conversion device which can convert electrical energy into mechanical energy. Okay, so now if you apply any kind of voltage, okay, suppose of course we should apply the operating voltage, and which will not beyond its threshold limit. Okay, so we have to apply the voltage, and after that you will get a certain speed. Okay, certain speed. But if you want to control the speed of the motor, so here you can see this is represented by a BLDC. BLDC stands for brushless DC motor. Generally in case of drone applications, if you want to design any quadcopter or the hexacopter, so at that point of time BLDC motor is generally used, whose RPM is nearly 1000 RPM. 1 kV or 10 kV motor are there. Okay, generally if you want to control the speed of that BLDC motor, okay, you should apply the controller. Okay, controller. So this is the PID controller. Okay, so here you can see that this is my reference input, which is basically the desired speed. Okay, desired speed. Okay, and here from here here you can see the this is the BLDC motor, that is called the brushless DC motor, where we have to apply three-phase current, three-phase AC current we have to apply, and after that we can get the speed, and we should control the speed of that BLDC motor. So the speed is represented by the angular position, which is represented by theta. To measure now, what I have discussed with you, that basic component generally used for the control system is the sensor, transducer, or controller. So these are, and also the actuator. So these are basically the basic components. So this is as actuator, this is the sensor, and this is the controller. So these components are generally used to build a control system. Okay, here you can see that suppose you use the speedometer or the tachometer, which is generally used to measure the speed of the speed of the BLDC motor. So from here it will compare the angular speed, and it will measure the speed, and it will compare with the desired speed. Okay, it will measure the speed and it will compare with the desired speed. So this is my actual output, and this is my desired speed, which is applied as input. Okay, so after that here from here you can get the error signal. Now this signal is basically propagate or process with the controller, PID controller, which basically generate the DC voltage. Okay, DC voltage from PID controller you will get the DC voltage. Now three-phase inverter is basically the power electronic converter that actually convert DC into AC, DC into three-phase AC. So three-phase inverter, so it will generate the three-phase AC voltage or three-phase current. Okay. So and after that it will process through it. So this will continue until and unless it will reach to its desired conditions. Okay. And also for controlling the speed, for controlling action or for triggering purposes, to trigger the switch, because this three-phase inverter is basically acts as a converter also. And here you can see that to triggering the switches like S1, S3, S5, and S2, S4, S6 simultaneously, you have to apply the commutation circuit. So this is my switch. This is my switching pattern. Okay. So here you can apply in MATLAB. In MATLAB, I think you can see from here. This is this type of design can be done in MATLAB. I will show you one by one, but here you can see that this is my desired speed. Okay. And this is my error voltage, which is generated from the control signal. And this one here you can see another thing, that this is called uh, Simulink to PS converter. Simulink. So because this is my Simulink block now, and this is the physical block which is under SimScap. SimScap. So Simulink is basically the platform where you can do that kind of model-based design. So this, if this is my network, this is my network, you can design that network in the Simulink platform. And here you can see, yeah, if you want to apply, if you want to add any kind of SimScap block from the Simulink library browser or the SimScap electrical library browser. Okay. So then you have to use the Simulink to PS converter. Okay. And after that you can see, you can see that the output ABC, the three-phase AC current can be generated, and it will fed to the BLDC motor. This is grounded. This is acts as a reference node. And for mechanical action, for basically for the mechanical actions, because I have to, as we have to measure the speed as well as the torque, because we need to know the speed torque characteristics of the DC motor. Okay. So we should apply the torque sensor and other mechanical component. Okay. So after that, if you simulate it, you will get that kind of output. Okay. And for switching pattern, basically we can apply some pulse width modulations. So yes. So this is the physical modeling of BLDC motor in MATLAB. Okay. So I think you got some idea. So if I am talking about the open loop control system and closed loop control system, how we can approach. Okay. So these things, I think you got some idea from here. Okay. Now I am directly moved to the MATLAB. Okay. This screen is visible, sir? This MATLAB screen is visible?
Yes, sir. Visible. Perfect.
Okay, okay, sir. Okay, sir. Now, first thing is the transfer function. Okay, I will generally move from basic to advanced. I will move to the transfer function. So transfer function is basically defined as the ratio. Transfer function is basically defined as the ratio of Laplace transform of the output to the Laplace transform of the input. You can say it as a, because it is very well-known term for the for control system. That is the already I have told you that this is 1 minute. This is the general model. Because here you can see that input and output. So output by input, you can call it as a transfer function. So basically CS by RS, it is it is represented in time domain. But if you want to represent the transfer function, that will be represented in frequency domain or Laplace domain. So CS by RS, if you transform the RT, if you transform the RT to the Laplace domain, it will be Laplace domain or S domain, it will convert into the RS. So RT will be RS, YT will be YS, and ET will be ES. Okay. So CS by RS, C stands for the control output. CS by RS is equal to the transfer function. Okay. So 1 minute. Yes. So here you can see this is my transfer function and for a second order equation. Okay. So generally there are different types of transfer function are there for different system. Okay. So first S plus 50. This S plus 50, I think it is represented by this is numerator and denominator. This is represented the poles and zeros. Okay. So here you can see if I for if TF equal to 0 uh, for which value or for which root the TF will be 0, then this root will be considered as the zeros of the system. Okay. So basically the zeros of any transfer function are those values of S which basically make the transfer function or basically make GS tend to 0 or equal to 0. I think you have understood. Okay. So for which values of 0 the transfer function will be 0. So this is considered as the zeros of the particular zeros of that system. Okay. Similarly, the poles. The poles is basically the values of S, because here you can see that S square plus 11S plus 12. Okay. So for which value of S the transfer function will be infinite. Okay. Transfer function will be infinite. So this is basically called the pole of that system. So here S minus 50, S equal to, if I consider S equal to minus 50, so for this value the transfer function will be 0. Okay. So minus 50 will be considered as the pole of the system. Okay. Similarly you can consider the zeros also. Okay. So here upper one is considered as zeros and lower is considered as poles. Or numerator is called as zeros and denominator is called as poles. Okay. So here first MATLAB example is that I can write the transfer function in that way. Okay. So here I am using the comment sign. Okay. Just a minute. Go to home section. Sorry, not go to home section. Live editor. Yes. So this is the live editor task. Okay. This is not script. Okay. This is basically the live script. What is the beauty of live script? That you can add equations here, you can add images, you can add text, or also you can add hyperlinks. Okay. So you can add this. This is the text section, and also this is the code section. Okay. So here you can see that this is my code section. Okay. So if you click on this section, you can insert the code section. Okay. Also there is other options are there, that suppose if you want to insert any checkbox, drop box, edit field, or the numeric slider, so you can add it from here. Or if you want to plot other type of apps like plotting or cleaning missing data, cleaning outlier, so if you want to add that kind of plots, you can that kind of apps, you can add it here. Okay. So here you can see in this live editor task, you can yes, in this live editor task you can see that this is the transfer function. So you here this is my coefficient. What is the coefficient of S? 1. And it is 50. So it is written here 1 space 50. And next S square plus 11 plus 11S plus 12. So S square, what is the coefficient here? 1. And the coefficient of here 11 and it is 12. So now if I want to display display the transfer function here, okay, so you can it's running. You can display the transfer function here, okay. So you can represent it the transfer function, and here you can use the TF is the built-in function. TF is the built-in function to represent the transfer function of a system, okay. Okay, next is the Laplace transformation. Laplace transformation is very, very important because we know that scientist Laplace is basically proposed that transformation theory. Okay, I mean, if basically the system may be represented, or if you consider any linear system having the input RT that I have shown to you, RT or and CT, which is basically the output of the system. So this kind of output input output relationship can be described by the differential equation. Okay, so now differential equation, we know that s square plus sorry, or ax square plus bx plus c, or sorry, d2x plus dt2 plus b dx dt plus kx equal to 0. So this is basically my second order differential equation. Okay, okay, it is represented here. So this is my transfer function tf. Okay, so if I want to display the transfer function, so here I can write disp disp, and what will be the value of g that will be represented here as we consider the transfer function to represent the transfer function here. Okay, next here you can see suppose I want to transform this equation, or transform this equation. Suppose I want to transform any function. Okay, so if you want to represent any function, you can use the @ sign. Okay, you can use @ sign. Okay, so Laplace transformation is basically like that way, that whatever be my function, that function can be converted into time domain to frequency domain. Time domain to frequency domain. And also, what is the advantage of the Laplace transformation? What is the advantage of Laplace transformation? Advantage is that it will convert the any algebraic equation into the any differential equation into the polynomial form. So generally, that higher order differential equation is difficult to solve. Okay, so so if you convert the higher order differential equation into Laplace domain, and that will be represented by the polynomial equation or algebraic equation, correct? So Laplace transformation here, it is helpful. Okay, so first here I have written here the CLC is basically clear the command window. So here you can see that this is my command window. So if I type here any command like date, okay, so whatever be my command, previous command, that will be cleared from this command window by using the command CLC. Okay, so next is the CLEAR, clear. Clear is basically clear the value in the workspace. Whatever the attributes or the values appeared in the workspace, that will be cleared from here. Okay. Next here CYMS, seems T space S. Can anyone tell me that what is the functions of SIMS? Functions of SIMS. SIMS stands for symbolic math variable. Okay, this is under the symbolic math toolbox. Okay, symbolic math toolbox. If you have any ambiguity or if you have this type of function is unknown to you, just type in Google that function name and MATLAB. Okay, just a minute. SYMS. Okay. Sims in MATLAB. Okay. Sims stands for the symbolic scale, symbolic math variables. Okay. So basically, Sims function is basically used to assign the symbolic math variables or symbolic scalar variables or the functions or the matrix variables. Okay. So here you can see Sims t space s. Okay. So so here you can see that this is my function. This is my function. This is the exponential function e to the power of 3t sine 6t. Okay. So here I am showing you just a minute. Laplace transform. Laplace transform. Because it should be known to you, Laplace transform. Yes, I think this is the table. You can follow that table. This table is important for you. Okay, you should keep in mind. No, that one. Yes, no, that one. I think it is visible. If it is not clear, I will share it later. Okay, so here you can see that this is the list. Okay, list of the function in time domain. Function in time domain. Here it is written one. If I convert into the 1 into Laplace domain, it will be 1 by s. This is the step function. T is the ramp function. T is the ramp function. It will be 1 by s square. It will be 1 by s square. Okay, it is wrong here. It will be 1 by s square. So in case of step function, it will be 1 by s. The formula is ft e to the power of minus st dt. Fs, this is by the formula. Fs, it will be represented in the Laplace form. Fs is equal to 0 to infinity ft e to the power of minus st dt. So if you put the value here, ft equal to 1 e to the power of minus st dt, then it will give the output 1 by s. Similarly, for ramp function t e to the power of minus st dt, it will be 1 by s square. Similarly, t to the power of n is n factorial divided by s to the power of n minus 1. Similarly, e to the power of at, e to the power of at is 1 by s minus a, and e to the power of minus at, Laplace transformation of monotonically decreasing, exponentially decreasing function. If we convert it to the Laplace domain, it will be 1 by s plus a. E to the power so Laplace of e to the power of minus at is 1 by s plus a. Laplace transformation of e to the power of at is 1 by s minus a. Okay. Okay. So here you can see, yes, here you can see that e to the power of at is 1 by s minus a, e to the power of at 1 by s plus a. So it is available in internet. You can see it from your end also. Okay. Similarly, here you can see that t e to the power of minus at is 1 by s square. So if you convert sine omega t, then it will be omega divided by s square plus omega square. Cos omega t is s by s square plus omega square. Okay. So I think you have some idea that if I want to convert now, this can be done by doing the integration in pen and paper. In pen and paper. Hello, sir. Sir, your voice is not properly audible. Could you please enter your message here? Okay. Okay, so this is the Laplace of gt. So you can write that function, and after that you can convert it. Similarly, for inverse Laplace, if you want to do the inverse Laplace, so you have to write the function I Laplace. Okay, so you can convert that transfer function into the time domain function. Okay, so if you do the inverse Laplace, so GS will be converted into GT. Okay. Okay. Similarly, here you can see that next is the to find out the DC gain of a transfer function. So here you can mention the transfer function. So first you have to write the sims s, because the function variable is s. So to declare the symbolic scalar variables or symbolic math variables, so you can write like that way, sims. Okay, so this is under the symbolic math toolbox. Okay, next here to find out the DC gain, you can write limit gs s comma 0. Okay, then finally you can find out the DC gain. Okay. Now next thing is that initial value theorem. I think it is known to you, but how we can write in MATLAB. So in case of initial value theorem, the limit s tends to infinity. So as the limit s tends to infinity, you can write like that way. Okay. So SGS SGS and limit s tends to infinity. Okay. So like that way you can write the initial value, find out the initial value. So similarly, in case of final value, the limit s tends to 0. So here you can write the SGS. Okay, like that way. Now this is important. Now it is come into the picture that poles and zeros of the transfer function. So how you can find out the poles and zeros of the transfer function? Okay, so this is important. Suppose this is my transfer function. Already I have shown to you that this is my transfer function. Okay, s plus 50 divided by s square plus 11s plus 12. Okay, so this is my transfer function. Now my objective is to find out the poles and zeros of the particular of that system. Okay, so poles and zeros of the system. So this is my transfer function. So if you just type here pole, pole, pole within bracket g, then you can get the pole of the system. Okay, so for which value of s, the gs or the transfer function tend to infinity, that is basically represented as poles. Yes, sir. Graph, sir. Hello, sir.
Dr. P.C. Thakur, is there any question? You are not perfectly audible.
Okay, sir. Okay. Next is the zeros. Zero is basically the zeros of the system. So zero is of course s plus 50. So this is s plus 50. So if s plus 50 equal to 0, s equal to minus 50. So for which value of s, the transfer function tend to 0. So this is basically called the zero of the system. So to find out the zero of the system, just you type here ZERO 0. 1 minute. 1 minute here. Yes. So you can type here the zero of the system, ZERO.
क्या बातें कर रहा है अपने आप मैं क्या कर रहा हूँ तेरी छोड़ है नहीं हुई
So this is called the poles of the system. This is called the zero of the system. Okay. Have you understood, sir? This
Yes,
is
sir. It's fine. Fine,
yeah,
sir.
okay. Now next thing is important. That is the how to find out the PZ map. So PZ map that is called the pole zero map. So till now we have discussed how to how to find out the transfer function, we have used the sims function. Sims function is constructing the symbolic objects or symbolic scalar variables. We have used the Laplace. Laplace is basically the function which basically finds the Laplace transformation of time domain function in time domain. So if you are handling any time domain functions, that will be converted into the frequency domain function by using the Laplacian operator. So just you use the built-in function Laplace, just you built-in function Laplace LAP LACE, LAP LACE, and to find out the time domain function again. So you can use
Sir, you are not audible. Dear participant, please stay connected. Speaker has some technical issue. He will raise your hand.
yes, sir.
Yeah.
Yes, sir. My voice is audible, sir.
Yes, sir. Audible.
Yes, sir. Actually, sir, network issue. Just a minute. So my voice, it is clear, sir, now?
Fine, sir. Fine.
Yes, sir. Yes, sir. Okay. Okay. So here I am. That is the PZ map. So basically here in MATLAB, now we have pole, we have zero. Okay, right? Now we want to map that pole and zero in a particular figure. Okay. So here MATLAB basically offers some several option to map poles and zeros of a transfer function on S plane. S is basically stands for the space, because we know in complex number that is represented by a plus of ib. So in case of S stands for the space domain. So S plus A is equal to sigma plus of j omega, where sigma is the real part and omega is the imaginary part, and j is basically the imaginary operator. So now if I want to map the poles and zeros of a transfer function on this S plane, or if you want to plot the location of these poles and zeros for the transfer function in the real and imaginary plane, because S is the combination of real plane and imaginary plane. So here you can see this is considered as the real axis, this is considered as the j omega axis, this is called plus j omega, this is called minus j omega, and this is the real axis. So I think it is clear. So this is imaginary axis, this is the real axis. Okay. So pz map, so in MATLAB here you can see this is just one line code, pz map. So pz map basically basically plots the pole zero map of the LTI, any kind of LTI model or any kind of continuous or discrete time model. Okay. So here you can see that if you just type here pz map and within bracket g is basically the transfer function. So then this command is basically help you to find out the pole zero not only the pole zero conversion, but also it will map it map it to this S plane. Okay, so here you can see plus 50 and 1 minute minus 9.7 minus 1.2. Okay, so here you can see that this is my pole minus 9.77 minus 1.20 poles. Here in this is my real axis, so this is represented by the two number of poles are represented here, and this is the zero is at minus 50. Okay, so here I think this is the in here you can see that this is represented the zero of the system, minus 50, 0 at minus 50. Okay, oh, just a minute. Now next thing is the damping ratio. Okay, damping is very important because any second order equation, suppose you are talking we are talking about the RLC circuit. Okay, so if we talking about the RLC series circuit, what will be the voltage equation? Can anyone tell me what will be the voltage equation? Any idea, sir? Any voltage equation? So basically voltage across resistor is V equal to IR, and voltage across inductor is LDIdt, and voltage across capacitor with that we know that is 1 by C integration of IDT. 1 by C integration of IDT. So basically for the if we talking about the second order differential equation, so then you will find that type of equation. Okay, so basically V equal to IR plus LDIdt plus 1 by C integration of IDT. Okay, now if you now this equation in time domain. Now if you want to convert in the Laplace domain, then it will you will find that S square plus L by R zeta omega ns plus I think I have forgot. Just a minute. If you would convert the voltage equation in Laplace domain. Just, okay. So this is basically the equation. Okay. So V equal to IR plus LDIdt plus 1 by C integration IDT. So if you convert it, you can see the second order differential equation. I think it will be mentioned somewhere. Okay. So this is basically the second order differential equation. Second order differential equation. Just a minute. Yes. Almost it is similar. So k omega n square plus s square plus 2 zeta omega ns plus omega n square. So if you compare, suppose you are applying, okay, you are applying any step response. You are applying any step response to the second order system. Suppose unit step response or unit step input of the second order system. Then you will find the CS by R is equal to omega n square plus s square plus 2 zeta omega ns plus omega n square. Now here you will find the damping ratio that is represented by zeta. Okay, so so here you can see if it is greater than 1, then it is called the overdamped system. If it is less than 1, then it is called the underdamped system. And if it is less than 1, if it is less than 1, then it is called underdamped system. And if it is equal to 1, then it is called critically damped system. Okay, so zeta is greater than 1, then the system will become more sluggish in nature. Okay, sluggish, or you can say it as the system is become slow in nature. So if zeta equal to 1, then it is called the critically damped case. Okay, zeta equal to 1. Okay, and for underdamped situation, here you can see that for underdamped situation, zeta should be lie between that 0 and 1. Okay, so here you can see that zeta equal to 1.5. Okay, zeta 1.5 means what? It is greater than 1. So then you will see that k omega is represented by like that way. Omega, this is the zeta, and this is my transfer function. Okay, you can display that transfer function is like that way. Okay, and you can see the step response. Okay, this is the step response. So on this transfer function, you have applied the step response. Okay, step G. Okay, so here you mention the omega value, zeta value, and you can create the transfer function. So this is my transfer function in case of overdamped system, where zeta value is greater than 1, I mean 1.5, and after that you have applied the step response. So just type here step, and it will apply on the transfer function, and you will get that kind of response. Okay, now the limit is 0 to 2.5. Why lim? You can limit your x-axis and y-axis by using the function ylim and xlim. Okay, so this is ylim. So limitations of the value in y-axis, limitation of value in x-axis. So this is confined in 0 to 2.5, within 2.5, and here the x-axis is 4.5. Okay, so system becomes sluggish in nature means after there is a transient response, and it will slowly reach to its steady state response. Okay, so from here, if you want to know the information of the parameters, so this is very important, because zeta is basically the ratio of the actual damping and critical damping, but some part is more important. Parameter is more important, because this parameter basically shows the performance of the control system. Okay, so I will show you some advanced example also, but here you can see from this curve, I want to know what is the rise time, what is the delay time, what is the peak overshoot, because you are applying the step response or to the overdamped system. Apply the step response, you are applying the step response. So here you have applied the step response to that overdamped system, correct? Overdamped system, and you want to know its response characteristics, transient response characteristics. So within transient response characteristics, you will find some basic parameters like delay time, that is called TD, rise time, that is called TR, peak time, that is called TP, or maximum peak overshoot, that is represented by MP. Okay, or the settling time as well as the steady state error. So these type of information you will get easily from by using the MATLAB command. Okay, so if you want to display the step info of G, I mean, you want to know the information of the rise time, transient time, settling time, minimum settling, maximum settling, also the any overshoot is there or not. As there is no overshoot or no oscillation which do not cross that line, so that's why no overshoot is there. So overshoot is 0, no undershoot is there, so that's why it is 0, and the peak value is 1.99, so almost equal to 2, and this is the peak time, that is the 5.1997. So now I want to display the PZ map here. So here you can see that the poles and zeros will be represented in the overtime case. So this is the overtime condition case. Okay, I think it is clear to you. I think it is clear. So from here you can see the pole zero mapping. Okay, okay. Next is the state space model, transfer function to state space model. So why state space is important? Basically, in previous any linear system that is represented by transfer function or block diagram. Now, if we consider any type of system like time invariant system or time variant system or MIMO system, that is called multiple input and multiple output system. In that case, the behavior, the system behavior represented by the state variables. Okay, so you have to determine the state of a system. So that is represented by the state space analysis or state variable analysis. Okay, so if you want to know the state of a dynamic system, you have to apply the state space analysis technique. Okay, and you need and this type of variables is basically called the state variables. Okay, now in case of transfer function, there is two type. One is the new if you represent the transfer function, there is one is numerator, another is called the denominator. Okay, now numerator is represented here. If you consider the numerator n equal to 2 divided by s square plus 20s plus 2, s square plus 20s plus 2, this is my transfer function. Okay, so this is my transfer function, 2 divided by s square plus 20s plus 2. Now I want to create the state space matrix or state space variables. Okay, because if I consider any kind of physical network like RLC network, okay, so if I want to represent by any kind of state space matrix, then it can be represented like that way. Okay, so I can convert any transfer function to the state space matrix, and this A, B, C, D is basically called as the system matrix. Okay, A is basically called the system matrix, B is basically called the control matrix. Sorry, B is B is control matrix, C is basically the output matrix. Okay, so basically the equation, equation is represented by the state equation format. So whatever be my transfer function, so if I want to convert the transfer function into the steady state model or a state space equation, okay, equation model, so you can use that inbuilt function that is called TF to SS. TF to SS that will convert that numerator and denominator to the state space matrix, where A, B, C, D individually, A, B, C, D's individually are the matrix. Okay, so where A is the system matrix, B is the control matrix, C is basically called the output matrix. So here you can see from this state space model, if you want to represent the ABCD, so you can type here state space SS equal to A comma B comma C comma D, then ABCD will be represented here. So this is the continuous time space model. Okay, so I think you got the idea how to represent the state space model and how to convert the transfer function to the state space model. So from here you can get, basically you can get the transfer matrix. Okay. Next thing is important, that is called the controllability and observability. So this is very important because here you can see that this is my state equation, x dot equal to ax plus bu and y equal to cx plus du, where a, b, c, d is basically the matrices of that particular equations. Okay. Coefficient matrix of that particular equation. So now next thing is that we need to know the system is controllable or not. Okay. So if when we can say that system is controllable, if the initial state can be transferred to the final state in a finite interval of time by some control u. Okay. So that time you can say that this system is controllable. Okay. So and when the system is observable, so this is controllable. So there is a matrix, a is one matrix. This is basically one matrix, a b c d control matrix, or the output matrix that is represented from the equation. Okay. So here you can see that a is the control matrix whose dimension is 2 cross 2, and b is another matrix which is basically represent the control matrix, and c is basically the output matrix. Okay. This is basically the output matrix. This is the row matrix. This is basically the row matrix that is represented by space. This is the column matrix that is represented by the semicolon. Okay. And this is the D. This is the D. So now I want to check the controllability and observability. So just to check the system is controllable or not, so just you type CTRB. CTRB stands for to determine the matrix is controllable or not. So from here you can check the controllability option. So if here you can see that rank of the matrix controllability. So from here you can check the rank of the matrix. Here you can see if you want to determine the rank of the matrix. So here this is my controllable matrix, and there should be some non-zero rows will be there to check that system is controllable or not. Okay. And here you can see that here we first find the rank of that matrix. So this is my matrix. And from here you can find the rank of that matrix. And next we check also the rank of the matrix A. Okay, which is basically the system matrix. Now we need to compare the rank of the A matrix with the rank of the controllable matrix. So if this is my conditional statement, that if this equal to this, then we can say the system is controllable. Okay. So first we may from here we can assign the A B C D matrix. After that we first find the controllable matrix that is achieved from the CTRB function. After that we check the rank of these two matrices, rank A and rank of the control M matrix. And next we equalize that if these two matrices rank are equal, then rank, it is not the matrix, it is the rank of the matrix. So it may be 2 or 3. Okay. So if these matrices are equal, then it is called controllable, and if it is not equal, then it is uncontrollable. Okay. Similarly, So this system is controllable. So this system is controllable. Okay. So you can check that there is a non-zero element is there. So the 3 rows are having the non-zero elements. Okay. Non-zero rows are there. I mean, if all the rows are zero, then it will be discarded. Okay. Similarly, you can check the observability also. So you can use the function that is called OBSV, that is for the observability, and after that you can check that matrix is observable or not. Okay. Now I am showing you. Okay. Now I am showing you the control designer app and PID tuner app. This is important. PID stands for proportional, integral, and derivative control. I think it is known to you. I think this screen is visible. So this is the this is the design engine design in the simulating platform. Okay. So here I am showing you, and from this example, I will show you how the PID tuner app will work to control the speed of that engine. Okay. I think this screen is visible. Speed control of PID block is visible.
Yes, sir. Visible.
Yes. Okay. Okay. So this is PID control block. Just click here and hit space. Hit space. Then this whole design will fit to that design. Okay. I mean the fit to that window. Okay. So basically this example shows how you can automatically tune a PID controller block using the PID tuner. So there you can see this is my speed reference. You know, no need to for now you no need to understand that kind of thing in detail. That is the induction to power stroke delay or drag torque. So this is not required for now. Okay. If I consider this is my plant, okay, this is my plant. So what is your basic what is our basic component? That this will be our plant. This is my controller. This is my reference input, and from here you will get the output. So, and to measure the speed of the to measure the speed of the DC motor, okay, sorry, to measure the speed of the engine, you can add scope here. So this is called scope here. So if you run the program and open the scope, just a minute. Okay, let it open. I'm just telling you that PID tuner is basically proportional and integral and derivative tuning tuner app, and this tuner basically provides for single loop tuning method, PID tuning method. Suppose here only one loop is there. Okay, so here you can see that this is the one loop is there. So before launching the PID tuner app, I want to show you that while the speed, any reference speed is given to that particular system, you will see the engine speed, which is basically showing the fluctuation. Okay, not in the stable condition. Okay, so you need to incorporate the PI controller, as well as you have to tune the coefficients of PI and D individually. Okay, so either you can do it manually, or by using the PID tuner app you can check the robustness. Just a minute, it is opening now. So main parameters, what are the main parameters? Okay, suppose if I am talking about the parameters, that is the settling time, delay time, rise time, peak overshoot. These are basically the important parameters. Okay, now I want to design design a system which should be controlled. Okay, where if I am giving you a challenge to uh, challenge that the machine should be, the system should be uh, system should be stable within 5 seconds. Okay, stable within 5 seconds or 4 seconds. So the settling time under 5 seconds. Okay, and if I am telling you that there will be no error. Okay, no steady state error. So ESS should be 0. So we have to tune the parameter in such a way that then it will achieve the ESS value equal to 0, or the settling time TS equal to 5 or less than 5. Okay, because if the settling time is more, then it will take more time to reach to its output state. Okay, so how you open this app? So go to the app section, in the drop down button you can click on it. Okay, so there is a section that is called the control system design and analysis app, control system designer app, control system tuner app, neuro fuzzy designer app, fuzzy logic designer app, diagnostic feature designer app. Diagnostic feature designer is also very important. PID tuner app. So these apps are helpful. You can just tune the parameter, and you can generate your model. Okay, so if you want to open the PID tuner app, here you have to write the PID capital T UNER, okay, in the command window, or you can directly click on it, and after that you can able to open the PID tuner app. Okay, okay. Next, just I am, as it is opening. Okay, okay, let it open. I will discuss other two app also. Okay, just a minute. Uh, 1 minute. Okay. Okay, you can follow that another app. I will show you the PID tuner app later. Okay, so this is one important app, that is the control system design app. Okay, so you can design the CISO system. CISO is the single input single output system. Okay, So to open the control system design app, okay, control system design app, you can use that. Yeah, either you can write the control system designer in the command window. This is in camel case condition. Okay, and here you can see, that this is my s equal to tf within bracket s. Okay, and this is my system s equal to 1 by s plus 1, and here I have written here control system designer. Okay, and sys. So this is my first order system. Okay, now I want to create the Bode plot for this particular system. Okay, so basically for the in stability theory, you will see that Bode plot is very important, where we have to find out the um, magnitude and phase for to know the stability of the particular system. Okay, so here you can find out. So here in control system design, you can see the edit architecture. Okay, so if you click on it here, you will find the different type of option. I will show you. Okay, I will show you in app. Okay, next there is a different tuning methods are there. Okay, and you if you create any transfer function like first order equation, any first order equation, one divided by 1 divided by s plus 1. Okay, and if you import it in the control system designer, then it will show the two plot. One is the magnitude plot and another is the phase plot. Okay, so in case of Bode plot is basically representing a graphical presentation of any transfer function to determine the stability of the control system. Okay, so here you can see that if you apply the step response for to that particular system, okay, you will get a what is the response that you will get, that is represented in curve. Okay, so basically one plot is the phase plot, another is called the magnitude plot. Okay, so these two separate plot will be there, and here in one plot here you can see that magnitude will be represented in dB. Okay, so in one plot, okay, it is opening now, just a minute, it's opening now. I'm showing. So in one plot, this is basically the logarithm of the magnitude of this particular transfer function, and other plot, that is in the phase plot, where you can plot the phase angle, and both is plotted here. You can see that both is plotted against frequency. Frequency is represented in radian per second. So this is called the angular frequency, not your not the frequency whose unit is hertz. Okay, okay, so it is the angular frequency where omega is equal to 2 pi f. Okay, so here you can find out that thing. Just a minute. Okay, yes, it is appeared. So here if you click on the edit architecture, you can select any different types of architecture here. Okay, so in tuning editor, there is different types of tuning editor. That is the Bode editor, or the closed loop Bode editor, Nichols editor, or the root locus editor. Okay, and different types of tuning methods are there. That is the PID tuning, optimization based tuning, etc. Okay. Okay. 1 minute. Okay. So from here you can see, yes, you can see you can add poles and zeros to the particular system. And here you can change the phase margin as well as the gain margin will be changed. Okay, so basically in case of phase plot, so which is basically the logarithmic of the magnitude plotting, and that is the phase plot that is represented by log omega. So from here you can get the two types of other parameters, that is the gain margin and that is called the phase margin. Okay. So here you can use the lead compensator. You can change the zero, pole, or the phase angle, etc. Okay, and also the frequency. So at frequency equal to 4. So this is the lag lead compensator. Okay, for the lag lead compensator, you can see how the gain margin is changed, how the phase margin is changed. So gain margin is basically the margin in gain which is allowable uh, allowable till the system actually reaches on the verge of instability. So this is called the gain margin. Okay, and phase margin is for additional phase lag. Okay, which can be introduced without affecting the magnitude plot. Okay, so it is basically the amount of additional phase lag which can be introduced in the system. So here you can see the different types of tuning method, or like optimization based method, PRD tuning method, LQG synthesis are there. Okay, so you can export the controller. You can export the controller to the workspace. Like that way, you can export the controller. 1 minute. So here you can see again. I am showing you that this is my controller, this is my system. Okay, so this is my system. This is the example of the speed control of an engine. Okay, I want to automatically tune the PID controller, PID controller using the PID tuner app. Okay, but how is it possible? That I am showing you. So first I need to, before tuning the PI controller, because PID, there are three coefficients that are there. I want to tune the coefficients of that controller, but before that I need to know that what is the response of that controller, of that system. So this is my response of the system. I think while the supply while the input is given, you can see that is my fluctuation, that is my speed response. Okay, so this is the initial speed response without modulating or without modifying the PID tuner PID coefficients. Okay, now my next objective is to tune the parameter. Okay, tune the parameter or tune the coefficients of it. Okay, so next I am click on the PI block. Okay, PI controller block. So while I click on the PI block, then this window will open. Okay, this window will open, and if you click on it, okay, so here it is written, this is the PID block. This block implements continuous and discrete PID control algorithm and includes advanced features such as anti-wind up, external reset, and signal tracking. Okay, so here this is my controller, this is my PI controller. You can select the PID controller. If you select the PID controller, then you can see that proportional control coefficient is 1, integral coefficient is 1, derivative is 0. Okay, you can select PI controller also. So here you can see only for PI controller, you can see the proportional coefficient is 1, integral coefficient is 1. Okay, so you can select the form here. Okay, this is my compensator formula. Okay, and okay, now there is a option that is called the select tuning method. Select tuning method transfer. There is two options. Is the one is the frequency response based, and other is the transfer function based PID tuner app. Okay, transfer function based PID tuner app. So you can tune it from here. Okay, so you have selected. If you want to open or tune by the PID tuner app, then you have to select that option and click on the tune. So click on tune. So while you click on the tune, then a window will open. So so when you click on the tune, this PID tuner app uh, app will be open, or PID tuner app launches, and basically this PID tuner shows the initial response, or basically the 1 minute. Oh, okay. Tune and then apply. Tune and then apply. Okay, I click apply. Okay, click apply to these changes and then tune. Achha, click apply to these changes and then tune. Okay. Click apply to it. Then tune. 1 minute. I think it is opening. Just a minute. So now it is obtained the planned model, realizing the planned model. So basically, this PID tuner computes initial PI controller to achieve a reasonable trade-off between the performance and robustness. So while you open the PID tuner app, you will find the option that is called the one is the response time. You can change the response time, and also you can change the transient behavior. Okay, so you can change the response time as well as the transient behavior of this plant. You can find that how much rise time or the delay time is changing as your objective. If I am saying that your objective is to settle the system output within 2 seconds, and my objective is to settle it with zero steady state error. So ESS should be 0, and the settling time should be less than 2 seconds. So if it is my objective, then I have to tune the parameter in such a way that I have to tune the response time or the transient behavior in such a way that we can achieve this goal. Just a minute. One minute. So how you can build that kind of block? Okay, so you can get all the system information from here. Okay, this is the gain block. These are basically the subsystem. Okay, if you click on it, you can see that other components are there to create that kind of system. Okay, this is the step response. Okay, or you can see as a reference input, speed reference input, and here error signal is generated, and this is the scope. Okay, this is the Simulink library browser. If you click on it, then you can find the different types of blocks here. Okay, it is not opening. I don't know why. Okay, we will jump into the other app also, because I will show you some okay, so this is the control system designer app that I am discussing in previous. So there are different types of architecture. You can see that edit architecture. You can if you click on edit architecture, you can find the different control architecture. Okay, so you can click on it. If you click on it, you can see the different type of architectural model, and you can also select here the tuning methods, different tuning methods. Okay, and you can export it. Why it is not opening, I don't know. Okay, I'm discussing other problem. Just a minute. Okay, I will show you. I will show you. Just 1 minute. Okay, 1 minute. 1 minute. Sorry, my actually in the model is heavy, so that's why example it's not opening. Okay, I will discuss discuss the other example here. Okay, I will share the experiment also. Yes, I will share the experiment as well as uh, documentation also. Okay. Okay, I am explaining one by one. So here, it is not openings, but if it is open, I will show that one. Okay, I will show this one. So just I am showing that some important experiment in detail. Okay, so this is the mass spring damper system. Okay, so if I talking about the any kind of practical system with its mathematical modeling, suppose this is the my mass spring damper system m d2x dt2 plus b dx dt plus cx equal to 0. Okay, cx equal to 0. So how you will open or how will create the that kind of model in the Simulink platform? First, you open the Simulink model and you can run the model like that way. So first here, this is my Simulink model. So I think it is visible. Okay, so if the equation is m d2x dt2 plus b dx dt plus kx equal to 0, okay, kx equal to 0. So if I convert it like that way, okay, cx. So here you can see that this is my spring constant, okay, spring constant, and here you can use the integrator. Okay, so integrator, suppose d2 x, if x is the angular position, then if you sorry, if angular acceleration, then if you integrate it, then you can get the angular velocity. And if you get the angular velocity, then if again you integrate, then you can get the angular displacement. So there should be the integrator. There should be two integrator which basically convert the angular acceleration to angular velocity to angular displacement. Okay. Similarly, if it is considered as x, then you can type here x. Okay, so this will be represented in in the Simulink model. Just I am showing that one. Okay. Uh, I think it is clear to you that suppose if I am doing the any transfer function, then I am representing the transfer function num equal to 1, 1 and den equal to 1, 2, 3. And if I want to system transfer function, then you have to type here sys tf num den. Okay. Now, if you want to generate any particular signal, like suppose step input. So step input, I mean, you know that ut equal to 1 while t greater than equal to 0 and zeros while t less than 0. So here you can see that if the time, okay, if the time this is the time, okay, and this is the step 0.01 step, and 0 colon 0.01 colon 10 means what, that this is the highest time, this is the lowest time, or this is the lower limit, it's the upper limit, and this is the step size. Okay, so the 100 I mean the 1 to 100, the all the values would be 0, and length time means this is the time of the length. So here for the positive time, in positive time, okay, the values of the values or the amplitude of the step input will be 1. Okay, similarly, like that way you can create the impulse input, step input, or the ramp input. Okay, ramp input. Now here you can see that if you apply the step input to that particular system, you will get the certain figure. Okay, okay, sir, sorry for the delay. So this is the Simulink model. This is my Simulink model where this is my speed reference, this is the controller, and this is the speed RPM, which will be output, which will be actually represented in scope. So if you open this initially while you run the program without tuning the PI coefficient or PID coefficient, you will get that kind of response, which is not the desirable response. Okay, now my objective is to get the stable output. Suppose my objective is to get the output where the settling time is within 2 seconds. Okay, within 2 seconds, and the steady state error will be 0. Then you can open the PID tuner app. So this is my PID tuner app, and here you can see you can either generate the transfer function or the plant equation, and you can import the plant model here. You can import the plant model, or you can directly import the Simulink platform. From the Simulink platform, you can import the plant. Okay. Now this is the response time. Here you can see that you can change the response time here to here. You can change the response time. Okay. And also you can change the transient behavior. Okay. And on the basis of that, if you click on it, you can see that some parameters will be shown. Okay. Okay. Okay, so you can change the response time and the transient behavior. Okay, you can change the response time and transient behavior, like and you will see the parameter is. So initially what you have observed, that initially the value of p is 1, value of for value of integral I is 1. Okay, value of p is 1 and value of I is 1. Okay, so if you click to the show parameter, then you will find out the rising time and the settling time. For a minute, sir. The value is not showing here actually. My computer is one. Because this is the 2023 version. So already already C drive is already occupied, almost 20 GB or 25 GB. The problem is that that kind of heavy model, if you try to run that kind of heavy model in your local computer, okay, local machine, so at that time that kind of problem you can face. So I think it is visible now that here you can see this is my PID tuner. So initially you can see the proportional value p value is 1 and I value is 1. P value is 1 and I value is 1. Now if you change the response time, or the transient behavior, automatically the value will be changed. Okay, so here at the left hand side you can see that if you click on that show parameter, you can see that rise time is 0.4 and settling time is 2.07, but overshoot is 18%. My objective is to minimize the overshoot. The overshoot is 18%. Now the overshoot is 10.4. If you change the transient behavior and see the result, the overshoot is 28.8%. So it is, while the transient behavior is more aggressive, the overshoot will be higher. Okay, so if you minimize it, or if you change the response time, then you can see the rise time, settling time also. Okay, so like that way you can find that at which point you will get your desired result. So here you can see that overshoot is 2.09, initially 224 point something, now it is reduced to 2.09. So you can change the transient behavior or response time in such a way that the overshoot will be almost 0 and the settling time will be less than 2 seconds. So if I give the value here like 3.1, or so now here you can see overshoot is 0.407, almost 0, but settling time is 3.45. I mean, the overshoot is almost 0, but settling time is greater than 2 seconds. So it is not required. So again, I can change the value. I can change the value and see what happens here. Okay, right now overshoot is high, 8.32%, but settling time is 2.95. So here now you can see that or settling time is 1.81. Settling time is 1.81 second and overshoot is 0%. So now it is okay. Now it is okay, because if my challenge is to settling time should be less than 2 seconds, then it is okay, 1.81. Okay, 1.81 second and overshoot is 0. So I can finalize this control parameter where this is my p value. So initially my p value is 1. Initially my integral coefficient value is 1. Now it is 0.14551 and 0.43791. Okay, so I can close it now and I can update the block from here. So click on here. So if you click on it, then automatically the block will be updated. So now again I move to the SCD speed control block. So this is my block parameter. So you can close it. You can close it now. You can close it now and check the block parameter value again. You can check the block parameter value again. If you click on the block parameter value, then the value will be updated. So automatically this, I think you have understood that how it will work. You can either import the your plant equation, or you can import the Simulink plant model directly to this PID tuner app, and you can update the PID coefficient. And after that, if you again simulate your program, then you will see the smooth response. Though it is not, it is actually taking so much time because my computer is not responding as lots of window is opened now. Okay. So I think this is the idea of the PID tuner app. I will share this example with you. Okay. And yeah, I will share this is how we obtain the pole zero map, Bode plot or Nyquist plot. Okay, so this is the how we can write that equation, transfer function. After that, you can just type here Bode or Nyquist to get the Bode plot, Nyquist plot, or the PZ pole zero plot. Okay. If you want to design any lag compensator for LTI system, linear time invariant system. Okay. So here you can just type the R value, L value, and the torque constant, back EMF constant. KB is the back EMF constant. RA is the armature resistance, and LA is the basically the inductive resistance. So after that, you can as it is a RLC circuit, because in case of motor control, you can see that these are basically the armature, where you will find the RA value, LA value, torque constant value, as well as the back EMF constant value. Okay, this is the moment of inertia, this is the friction constant. So you just assign the value, and after that you can create the transfer function, that is num comma den, and after that you do the Bode plot for this uncompensated system. So now if you apply the lag compensator, you here type your desired phase. So this is your desired phase. Okay, so you apply the desired phase angle and also the phase margin. So this is your phase margin, and this is the phase angle for the new phase margin. And after that you can create the lag compensator, and you can get the pole zero of this lag compensator. And while you apply the lag compensator or the previous transfer function, you will get the output. Okay, you will get the compensated output. Okay, so this is how you can design the lag compensator. Okay, so this is how you can see the uncompensated system and the compensated system. Okay, compensated. So this is your general output. Okay, and this is my compensated system. Similarly, if you want to model and simulate armature control DC motor, means what? That you want to the armature current basically control the DC motor. Okay, armature control DC motor. So here you can either connect the rheostat. You can do the rheostatic in control. Okay, so there you can this is the damping. Okay, this is damping. So if you want to control the resistance, if you want to control the speed of the motor by using the armature control action, so that thing you can do, right? Similarly, PID control action for the DC motor, you can um, see that this is my motor simulating model. Okay, this is my motor simulating model. So this is my reference input step voltage. I mean the DC voltage will be applied here. Then it will reach to the PID controller. Then from here you can get the control DC input. So DC voltage will be provided to the DC motor, and if you open it, you will find the simulating model of the motor, and eventually you will get that velocity, which will be acts as an output. And after that, if you want to control the speed of the DC motor, then you have to create that feedback path or the closed path. Okay, if you want to incorporate any disturbance, you can apply other type of signal here. Okay, so like that way you can create the Simulink waveform, Simulink based PID controller model. Okay, so this is the PID controller model. Similarly, for advanced application, like suppose UAV application, in case of drone application, you can use the closed loop system. This is basically the drone model. Okay, so suppose I want to do the VTOL. VTOL means vertical takeoff and landing. Okay, so for controlling the quadcopter motion, you will find the you will find the block from the UAV toolbox. Okay, UAV means unmanned aerial vehicle. You can say it as an unmanned aerial vehicle, or you can say it as a drone. Okay, now basically here you will find the two types of control. One is the there is two type of actually sensor are there. If you use the any drone, this generally the Picksock controller are there. Okay, so in Picksock controller there is called gyroscope and accelerometer are there. So and also other type of sensors are there, which is basically control the azimuthal angle, control the altitude, okay, or the XY control. So there is a gyroscope that actually check the XY movement, okay, desired XY movement. So movement command should be there, should be there, okay, and also the yaw, pitch, roll. So basically controlling of yaw is more important. Also the altitude control, if you consider the vertical takeoff, okay, vertical takeoff or landing, okay, so while it will rise from that 10 meter from the ground station or 20 meter from the ground station, so at that time you have to control the parameters like roll, pitch, yaw, or the thrust. So at that point of altitude control, these parameters are very important. Okay, so this controller will be fed to the um, uh, fed here as a parameter, and it will control the propeller speed. I mean the where BLDC in case of UAV application or the quadcopter application, you will find the BLDC motor, that is called the brushless DC motor, which will rotate at very high speed. Okay, so that at that time basically the propeller propeller movement should be controlled properly. Okay, so how it will turn, how it will move forward direction or backward directions, that will be controlled properly. So speed should be controlled. Okay, and so here you can use some control action. Okay, PID control actions or adaptive fuzzy control or hybrid fuzzy control action you can incorporate here. Okay. So I think, hello, sir. Sir, shall I stop or continue this session?
Uh, Sir, it is time to conclude the session now.
Hmm.
Yeah, if you need to present the code for the demonstration, please do it, and after that we need to conclude the session.
Yes. Sir, I will share the design with you because I think some apps while you basically I am facing a little problem because while you want to import any heavy plant model, this is my engine model. While you want try to import any heavy plant model, at that time the system may not respond. Okay. So my suggestion to all the participants, minimum, if you are using the MATLAB, this is the MATLAB 2023A version. Right now I am using. So in case of 2024A version, MATLAB, I mean the system requirement is I think 8 GB RAM. I think 8 GB or 16 GB RAM is there. 16 GB RAM is better, but 8 GB is recommended. 8 GB RAM is recommended. Okay, so this is important, and also there should be the SSD. I mean there in your laptop or in your machine. Okay, so I will share this type of documents here. Okay, and another example that I mean the resources that I want to show that you can go to the MATLAB documentation page. I think it is very. You can go to the MATLAB documentation page, and here you will find the control system toolbox. Just you can type in the Google. You can see the control system toolbox, and the control system toolbox, fuzzy logic toolbox, fuzzy logic toolbox. So these, and also Simulink control designer. I want to show the Simulink model in the using the Simulink control designer toolbox. Okay. Uh, so this Simulink control designer toolbox is basically helpful for Simulink model. Okay. So sir, I want to conclude my session. If possible, you can give a, if any, I mean, any participants are interested to know more in the control system, then I can.
The discussion, if you have any question, please feel free to ask.
Mhm.
Dear participant, if you have any question, you can unmute your mic for open discussion. Yes, please. Or either you can raise your hand so that I can unmute your mic.
Participants, please follow this documentation page. It is very helpful for you. Okay.
Sir,
This is
provide all these content along with the documentation so that we can share with the participant. And
definitely.
yes.
But sir, this is available in the MathWorks website. MathWorks website, you can see the link, that is a mathworks.com. Okay, you go to the documentation page, and here you will find the control system. Okay, control system toolbox. Okay, this is visible, na sir, from your end. This is the control system toolbox.
Yeah.
Okay,
but sir,
so you
if
can click on the control.
Sir, if you can provide the link of all these documentation, because sometimes
Okay.
participants are not able to access everything. But if we have the link, you can add all these in your presentations so that participant can access easily.
Okay, sir. Okay, sir. Definitely, I will definitely share with you. Okay, I mean the code the tool. First of all, the user guide of the toolbox. This is the important because the control system toolbox is very, very important. And
Hmm.
also the apps, because apps are very helpful. That is the control system designer app. I am showing them the control system designer app, control system tuner app, PID tuner app, and for basically for the advanced application like fuzzy logic toolbox. So these 4 or 5 control system toolbox are there, and for UAV and robotic application, it's like ROS toolbox is required. Robot operating system toolbox and ROS toolbox is there required. And for if you are interested in drone application or UAV applications, then UAV toolbox is required. So these are the basic toolbox for control system application. Okay, and so that documentation I will share, and also I will share the codes. Basically, for time limited time, I may not cover the whole code. Okay, so some 2 or 3 models that I try to show, but it is not possible in this time.
Yes,
Okay.
sir. I
So I will
we
share that
understand.
code.
Ji, ji.
Okay, sir. Okay, sir. Thank you, sir.
Thank you, sir, for a nice presentation. And the content are really very long, because when we try to this type of the simulation, lot of time is required. But we have limited time. That's why only we have 2 or 3 examples be presented during this session. And some more examples I recommend you to provide us so that we can share with the participants who are working in this domain. So thank you once again.
Definitely, sir.
Thank you very much to share your valuable thought on control theory. And all these are very helpful to the uh, researchers, scholars, and faculty members who are working in this domain. And I hope that this session is really very wonderful, informative, knowledgeable to all the participants who are attending this session till now. And tomorrow we will join at the same time. The speaker will be Dr. Shalu, because today we interchange due to some technical issue. Okay, so thank you very much once again to all the team members and today's resource person, Pickon Majumdar, Mr. Pickon Majumdar, a nice presentation, and we are very thankful to you for this valuable time. The feedback form and quiz will be shared in the WhatsApp group. You need to submit entire feedback form as well as the quizzes for each session to get your certificate of participation. Thank you very much for the today's, and keep patience in the coming sessions also. Thank you. Now it is time to end the session.